Okay, so in order to begin this class, I want you guys to really focus on this video that we're going to be watching right now. So I'm just going to make it a little bit bigger and I'm going to play it. Now, keep your eye on this video and I want you to have a good think about what this represents in terms of scale or ratio, okay? And where you can actually see that representation of scale and ratio. So watch this scene. Okay, there we have it. So I'm just going to quickly close this up right now. Okay, so now that you're back, I'm hoping that you said that this was a good representation of scale because the White House happens to be a scaled model that is 1:24 in size. Now, if you have a look closely on the right-hand top corner of the screen, you'll definitely see that there is a man who's actually the model maker physically creating this model so that it can be blown up for Independence Day back in 1996. So I'm hoping you guys said that. Okay, so thumbs up to those that did. Okay, so let's get on to the topic, how to calculate true scale and area. Okay, so this is very important because it will be on the exam and I want you guys to really focus on this and do the exercise as per instructed. Okay, so let's have a quick look at scale. Now, if you have a look at these images, and unfortunately because of the way PowerPoint works on this platform that I'm recording in, it's not allowing us to see the images as I want you to see it. However, scale, if I give you the quick definition of it, scale represents in proportional dimensions a reduced or increased size according to an original or true scale, which is essentially 1:1. So just to give you a bit of a example, 1 meter is to 1 meter. Okay, that's 1:1. 1 centimeter is to 1 centimeter. Same thing in millimeters. Okay, so that means that whatever that scale is on that side is going to be the same on the other, which means it is true scale. Okay. Now, this image of the Sydney Opera House is actually showing you models that is 1:69. And I know you're probably chuckling right now because you're hearing, what, miss, did she just say that? Seriously, kids. Okay, so these models, unfortunately, you can't see the ones behind it, but I'll give you a bit of a description of it. One is actually the physical model that was first conceptualized. The second one is actually a cross-sectional view of the inside or the internals of the Sydney Opera House. And of course, the one that you're seeing right now in wood, that was actually used by engineers to determine the aerodynamics of the Opera House. And yes, all these models were all represented in 1:69. So that's 69th the size of the real deal. Hopefully you guys understand that, okay? So, ratio. I want you to have a look at, so I want you to answer those questions. What do you notice when the size of the TV changes, okay? Does anything stay the same? I'll give you guys about a minute. Pause this video right now, okay? Pause it right now and answer those questions. Write them down. Okay, so I am hoping that you actually notice that the viewing ratio, or what they call as the aspect ratio, actually does not change. So every single time you change from a different overall size of the TV screen, it actually doesn't change the viewing. So you'll find that on the top left-hand corner there in red, that is actually your ultra-wide screen. And then you've got your 55-inch TV in the 16:9 ratio. And then, of course, you've got that one in the bottom there, which I'm going to move aside, which is actually kind of like the old school TVs and the old school monitors when they've used 4:3 ratio. Okay, I think you're probably too young to actually know those sort of sizes. What you're probably used to is definitely your full widescreen and your TV widescreen in the 16:9. Okay, so ratio and scale. I want you guys to now have a really deep think about real life examples of ratio and scale. We now had a look at aspect ratio with TVs. We've had a look at models, so miniature models. Think of other things that you can actually think of in real life where we have to use scale and ratio. Okay, I want you to divide that page up into half, put a title on ratio, put the second title on scale, and I want you to write down as many as you can. I want you to really think about this. So I'll give you guys a couple of minutes to do that. Okay, so pause this video, set a timer for 2 minutes, and all is good. Okay, so if you're still a little bit confused about the differences between ratio and scale, I guess just to give you a bigger picture, because we're focusing on the building industry, we need to focus on building scales, okay? So these are what is represented on two-dimensional form in drawings that we have seen in term 3, okay? In house plans. So if you can click on that link, open up your PowerPoint slide, click on this link and have a go with those exercises. They're quite simple. So I think you guys will smash this out in a couple of minutes, okay? So again, pause this, time yourself for a minute. Okay, so why do we need to know this? I know that's what you're probably wondering. Miss, why do we need to know this? Well, we have an exam in literally 3 weeks. So I want you guys to really, really focus in this first week, because I'm trying to get this all smashed out so we don't have to repeat it at all in the next 3 weeks. Okay, guys? So we need to know this because plans of buildings or house plans, okay, need to be drawn to a scale that we need to understand. Okay, so for an example, if you're going to be a chippy one day, you'll need to know the wall lengths, okay, and the wall heights from a plan in order to determine the distances between your framing, right? Makes sense? So we tend to use scale, so we can actually draw the whole building on a certain size piece of paper while still showing all the required details. So for an example, if you're a plumber, you'll need to know where all the location of your outlets are, the inlets need to be, etc. Okay, for the rough-ins and the final fit-offs. Otherwise, where's the pipe going to go? What happens if it's offset by, a meter? My gosh, that means that your toilet's going to be in the bedroom. So that's why it is important to know and read house plans and scale. Okay, so common scales used in building plans tend to be 1:100. Okay, that's usually for residential buildings, 1:200 for larger buildings, let's just say larger commercial lots, larger residential buildings that are mansions, okay, and then 1:500 is for things that are really big. I'll give you an example. Let's just say high-rise apartments. Burj Khalifa would have used 1:500, which is essentially the tallest building in the world. Goodness, even big plots of land, or even if it's a subdivision of a massive 44-hectare plot of land that's being developed. Think of Springfield Central. This place used to be all forests, and now it would have been on a site plan in 1:500. Imagine that. So if a plan is drawn to scale, a builder can actually measure a length on the plan using a ruler, okay, and use the scale, the physical scale that's represented in the plan to calculate the actual measurement of the building. So this is actually relevant if there are actually no measurements on the plan to begin with, okay? But there's a representation there of scale. It's also very useful if the plan itself happens to be printed out and there's some measurements missing. So you want to be able to determine how far that window is from that wall. Maybe you can move it a little bit more to the left, or maybe move it over to the right a bit. So these details are absolutely vital. Okay, put yourself in your parents' shoes. If they've renovated in the past, you'll know exactly how important house plans are for the planning stage of a renovation. Okay, so this is where we are going to learn how to calculate area of a scale drawing, okay, because this is really important. But first of all, we need to be able to know exactly what the physical measurements are on the drawing, okay, from what is represented in this particular plan. Because we know that from here to here, it's not going to be 6,000. We don't know how we're going to draw this, but we have a scale, okay? So we should be able to change this into a drawable scale. So here, first thing we need to do is determine the scale down dimensions for drawing. And then we're going to calculate the combined area of both area 1 and area 2, which are essentially rooms. Then I want you guys to do 1:250 and 1:50. And I want you to all show working out. So I'll give you an example. So you'll see here, we've got area 1, okay, which is represented with length of 6,000, okay, which is represented at the bottom of area 1, okay. We know that the scale is 1:200, so we need to divide it by 200, which equals 30 millimeters. So we'll be drawing this on a sheet of paper at 30 millimeters. Simple, yes. Now, we know the width is 6,000 as well, as represented on the left-hand side of area 1. And again, the scale is 1:200. So we divide that by 200, which also equates to 30 millimeters. Now, if we measure the overall length, 10,000, which is right at the top, okay, divide that by 2,000, you get 50. Again, the short width, which is that little L-shaped cutout, 2,000 divided by 200 equals 10 millimeters. So that's area 1. Now, area 2 dimensions is 4,000 by 4,000, okay? So we know that it's 4,000. Let's calculate the length and width. So the length ends up being 20 mil. Same thing with the width, 20 mil. Then we do the total for area 1. Okay, so that is length times width. Area 1, length times width is 6,000 by 6,000. So that ends up being 36 million millimeters squared. But do we work at that sort of figure? That's something that we're going to show you later. So area 2, again, length times width, okay? 4,000 by 4,000, we got 16 million millimeters squared. So therefore, the combined total area, if we add those two, so 36 million plus 16 million equals 52 million, okay? But let's note that we can convert this to something that is easier to use and understand for all calculations. So in terms of area, we'd like to convert the millimeters into millimeters, into meters, my bad. So 1,000 millimeters is equivalent to 1 meter. That's what that ratio represents, okay? So for every 1,000 millimeters, you get 1 meter. So here, we then divide this into 1,000, and then we get 52,000 meters squared because we are working with areas as our SI units, okay? So I want you guys to do 1:250, okay, and 1:50, and hopefully this should take you a good couple of minutes. So pause this, set a timer for 5 minutes, just to give you a little bit of time so you can look at this, okay, in terms of the way it's all set out. I want you to show working out as best as you can because that's what the exam is going to be asking for. So pause this right now, set that timer, 5 minutes. See you soon. Okay. So now that you've done that, I'm assuming that you're very successful. You're very happy with what you've done. I would like you guys to do this for homework. Practice makes perfect. Okay, it is all about process, it's all about method, and I would like you to calculate, or I should say determine the scale down dimensions for this drawing. Now, the scale provided is 1:250. Then I want you to calculate the total combined area of the right-hand bedroom and the lounge dining combined. Okay, so that is on the right-hand side as you're looking at it on the screen, and that room in the middle. Okay, there you go. So, folks, good luck. Don't stop working, and I will see you next week. Ciao.